Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now.
Good morning, good evening. Hi, my name is Stefan and I'm your moderator for today. And before we kick off with our first talk of today, it's time to say thank you. First of all, we want to thank you all of our partners, especially our main partner, Creo. After that, what would be an event without good media partners? So thank you to all our media partners. And last but not least, the people who are in our heart, our community. So also thanks to our community partners and dear friends. And before we kick off this third day, that's right, you made it to the 50% mark, we will have to have a look again at the code of conduct, which is more or less behave or. So, there is one more thing before we jump right into the action. There is a live discussion section on, wait, I always mess up, these sites where this thing is. It's somewhere at the bottom. There is a live discussion session. You can use the chat there to get in touch with other people. You can use that for Q&A. And yeah, use it, please. That being said, now we come to the first talk with Simon Stiebel-Lehner, and he will be talking about effective machine learning, managing complexity with MLOps. And if this doesn't sound Chinese to you, then you are in the right place. Simon is definitely no foreigner to this. He's a lecturer for data mining and data warehousing at the University of Applied Science. And because this is a University of Applied Science, it makes sense that he's also the expert machine learning engineer at bol.com. If you do not know what this is, you've never been to any of the Benelux states. So without any further ado, let's welcome Simon on stage. Hello, Simon.
Yes, hello, good morning.
So I say have fun, and I'll be somewhere in the background listening, and enjoy. Stage is all yours.
Perfect. Thank you very much. Good morning also from my side, and welcome to this talk about effective machine learning, managing complexity with machine learning operations, MLOps. My name, as you've already heard, is Simon Stiebel-Lehner. I must correct Stefan a bit. I'm now at the Transaction Monitor Netherlands and leading the MLOps team there. So I'm lead machine learning engineer at a fantastic company that's devoted to battling money laundering at a global scale. And next to that, I'm still teaching at the University of Applied Sciences, Vienna. Anyway, in the next 45 minutes, roughly, we will dive deep into the topic of machine learning operations, MLOps. We will start off by first building an understanding why machine learning operations is actually important and what it is. Subsequently, we will dive deep into the field using a case study. And in that case study, we will learn how we can lift our machine learning development process to the next level by introducing machine learning operations principles and tooling. But before we do that, we need to travel back in time a bit. To be precise, well, 9 years, almost a decade ago, Harvard Business Review published an article titling "Data Science is the Sexiest Job of the 21st Century." Right, and I'm quite sure that you have heard that sentence. Well, what's fascinating about this is looking at it from the year 2021 is that 10 years have passed, a decade has passed, and in tech, a decade that's almost eternity. A lot happens here, and this really shows that data science and machine learning, they are not the new kid on the block anymore. They have been around for quite a while. Fortunately, also a lot has happened in these 10 years. For example, looking at education, universities have been ramping up their study program, offering really bachelor and master programs in machine learning and data science, so they can really output highly skilled people that know how the field works. Also, on top of that, Python has become the lingua franca of data science, and within Python, an incredible tooling ecosystem has emerged. Yeah, naming just a few of them, I'm sure you're quite familiar with quite some of these packages, such as TensorFlow, Scikit-learn, PyTorch, and so on. Last but definitely not least, also business adoption has grown tremendously. According to a McKinsey survey from last year, 1 out of 2 organizations they surveyed said that they implemented machine learning or data science in at least one business function. And that's really a lot. That's a tremendous increase over the last years. So looking at these 3 points, right, we have skilled professionals, we have a mature tooling ecosystem, at least when it comes to data modeling and data processing, and machine learning and data science is also applied in practice. You could really think that this field has grown up. Yeah, in the last 10 years, so much has happened. It's a grown-up field now. However, on the other hand, still, and you have probably heard that a lot of times as well, or perhaps even you can see that in your own organization, still an incredibly large share of organizations fail to get value out of their machine learning projects, or even a lot of machine learning projects just fail before they even get the chance to deliver value. Yeah, and looking at this slide, that's quite weird. On the left-hand side, we seem to have a very solid foundation for actually getting value out of machine learning. But then on the right-hand side, we see that somehow organizations often do not manage to do so. So of course the question arises, what is the problem actually? What is the issue we are facing here? And to be fair, well, there is not only one issue, right? There are multiple. But one of the big ones, one of the really big problems that holds organizations from gaining value out of machine learning is that when organizations think about machine learning, what they usually think about looks like this, right? They think they hire a data scientist, they build a model. The data scientist, does some experimentation, he evaluates some models well, and then the problem is solved once that model hits some accuracy goal. Well, to be fair, there is at least one problem solved, which could be the modeling problem, right? If you have a model that's sufficiently good, you can consider that solved. However, definitely your business problem is not solved. In order to really solve your business problem and therefore get business value out of your machine learning model, well, you need to go further. You need to take that model to production. And that involves a few more steps. You need to productionize your model. You need to test your entire machine learning system. So that includes code, data, and your model. Then you need to deploy it and actually keep it running and continuously monitor and observe what is happening. And at some point, you will discover, well, your model just doesn't work anymore as expected. And this is the point where you probably need to go back all this way, tweak the model, do some changes, perhaps retrain or only retrain, and then move through all these stages again. So we see, in order to really produce value with machine learning, you need to go through this entire long process. You actually need to ship to production, and you need to monitor and be able to retrain and iterate fast. Well, it turns out this process is not only longer than what organizations typically think about, but it's also significantly deeper. Yeah, that means at each of these steps of this long circular process, we need to deal with artifacts, and that artifact is not only code, right? We know how to deal with code. We've learned that from traditional software engineering. That's not the big topic. However, each of these steps also produces or consumes models. That could be one model, but that could also be hundreds of models, and data. And the data can be big, that can be small, that can be changing, and come in a variety of different formats. And we need to make sure, if you want to go through this process, and if you want to deploy machine learning models to production successfully, we need to make sure that these artifacts are created, stored, managed, versioned, and consumed at the right point in time throughout this process. So we can see, well, taking a machine learning model to production and keeping it running at a high quality, and therefore enabling to create business value, well, that is a complex process. That's by far not as easy as most organizations think. And out of this complexity, typical problems arise. Problems I'm quite sure you've read about, or probably you've seen them in your own organizations. These problems are classic reproducibility. How can I make sure that I can actually reproduce the experiments that I've conducted? Yeah. Or consistency. How do I make sure that my training pipeline and my inference pipeline, for example, use the same pre-processing steps, even if I frequently change certain parts? Then, well, comprehensive testing, you do not only need to test code, but you also need to test your model, for example, for bias, and ideally you also test your data. Of course, once things are tested and you have your model productionalized, you also need to think about deployment. And of course, one thing are deployment strategies. Sometimes in machine learning, you would favor going perhaps for a bit more exotic deployment strategies, such as multi-arm bandit deployments, and you should be able to support those. But you also need to think about what hardware do I actually need at what point in time to deploy my model and keep it running. That can range right from theoretically a cluster of GPUs all the way to an edge device. So the bandwidth is very broad there as well. Once things are deployed, it doesn't stop there. Then the big challenge of monitoring your model appropriately arises. That means, well, you do not only need to monitor uptime, downtime, response time, but you also need to monitor data that goes into your model, for example, feature distributions, and also the output distribution your model produces, or perhaps, if you can, even prediction accuracy. At some point, inevitably, you will see that accuracy drop, or you will see things in the distributions changing. And at that point, you need to consider retraining. That means you probably need to go all the way back this circle and go through this circle again, or you just retrain the model. Well, ideally, that would happen in an automated way, because otherwise your data scientist might get a bit bored. So we can see, right, this is a complex process, taking a machine learning model to production, keeping it there, and frequently there are very typical problems that arise from that, challenges. So the big question is, how do organizations handle this complexity? How do they actually do that? Well, in short, most organizations, they don't handle this complexity. Yeah, they don't handle it because some are not aware of it, right? They might have started a year or two, or maybe three years ago with machine learning, and they have just not built the understanding to recognize the complexity of this process and what it requires to handle it. Other companies might recognize it, but they lack the technical abilities to actually handle it. The bad news is, well, not handling this complexity is simply not an option. It's not an option if you want to create business value with your machine learning endeavors. Because, well, if you do not handle this complexity, what you're going to face are things like the deployment gap. That means you're going to have 20 POCs lined up, but not a single model in production. Then your model and the process you need to go through in order to productionalize your model and keep it running is highly inefficient. It's highly laborious manual work. That's not only going to make your data scientists very unhappy, but also this means that your process is quite error prone. Right, you're dealing with this complex process, and then you have lots of human steps in the middle, probably a few handovers. It's inevitable that you will face quite some errors throughout this process. Eventually, all this means that your iterations, your development iterations, will be very, very slow. It will take you months, and perhaps, and unfortunately, that's no joke, even a year to take a model from experimentation to production. And this really is what kills machine learning delivering value. Machine learning is a highly iterative process. It's an experimental process. You need to be able to take models to production quickly to really learn how your model works in production. Every data scientist who has done that will confirm that in production, data might look a bit different. You might discover, oh, well, that feature I've been using, suddenly it's not really available all the time in production. And all these are things you only learn when you actually go to production. And therefore, fast iterations, being able to go from experiment to production and back to experiment and again to production, is really key to creating models that actually deliver value in production. Well, fortunately, in the last few years, a relatively new field has emerged, and this is the field of machine learning operations, MLOps, which is essentially the application and a bit of adaptation of DevOps principles to the field of machine learning development. And MLOps really has the objective to make this process going from experimentation to production as easy, as quickly, as robust as possible. And it does so by drastically increasing the degree of automation you see throughout this complex process, and therefore enabling you to actually iterate faster and also ship with improved quality due to the increased standardization you introduce by applying wide automation to your process. That sounds great, right? At that point, you probably think, yes, that sounds awesome. I want to buy that. How much does it cost? Well, the bad thing is it's not that easy. But let's jump into a case study and actually see how that can work. We are going to follow a fictitious company here. That company is called Acme Inc. It's an industrial company. They produce, in our case, high-performance tire. Doesn't really matter though. And we are going to follow that company and observe how they lift their machine learning development process to the next level with machine learning operations. And we are going to do this in 4 steps. First, we're going to sit down with the data science team and analyze how they actually currently develop machine learning solutions. Probably you are going to see some similarities to the organization that you work in here. And subsequently, we're going to sketch out what could an ideal development process look like, an MLOps enabled process. And of course, how can we define a tech stack that supports this process? Finally, well, we still need to define a transition strategy. So how are we actually going to execute our plan? How are we going to move from the what we currently have, the current state, all the way to our objective state, to our objective process that should enable us shipping faster, shipping more reliably. Before we dive into these 4 steps, let's take a small step back and first learn a bit more about Acme, get a bit more technical context actually to enable us understand the challenges at least a bit better. So from a tech perspective, Acme manages their own data center and they run a Kubernetes cluster in the data center. They develop all their company internal software with using Java on the backend, React on the front end, and they deploy them. They deploy their software as microservices in their Kubernetes cluster. Well, of course, they know that, Acme produces tires, managing their own Kubernetes cluster, managing their own data center. That's something that's just not really their core capability. So they know, all right, we want to move to the cloud. Our objective is in the next 2 years, we want to migrate everything to the cloud and actually become a cloud native company. In our case here, on AWS. And I think here it's important to note that throughout this case study, we're going to see AWS a lot. But of course, essentially what we are going to see is basically also able possible to do with any other major cloud provider, right? So it's not a specific AWS advertisement. From a data science perspective, well, they have ramped up the data science effort over the last few years. They've hired a data science team, to be precise, 6 data scientists. And these data scientists, they use Python for their data science and machine learning work. So far, they have deployed one model that's running in production. It's running in a microservice on the Kubernetes cluster that's doing some anomaly detection. Okay, so much on the tech side of Acme. So you probably got a bit of an idea of what's happening in that company right now. Well, let's now sit together with the data science team to understand a bit better how they currently actually develop their machine learning solutions. So we meet up with the data science team. It's assume it's post-COVID, so we meet up with the data science team, and we get into a large meeting room, and there is this massive whiteboard, and the data science team, they start drawing on that whiteboard. They really start sketching out their process, what they're currently doing, how they are working, and what they sketch out kind of looks like this. So we can see they are basically having these 3 phases. They're having an experimentation phase, then they productionize, and then they deploy to the cluster, and the serving happens there. That's kind of the big 3 phases. Diving into that in a bit more detail, we can see on the very left their machine data. They host that on Amazon Redshift, which is AWS data warehouse essentially. And the data scientists get the data from there using SQL, pulling that data onto their local computer where they have a local Jupyter Notebook instance running. There they do the exploratory analysis, some statistics, some model training, some experimentation, and at some point they are happy with that model. They have reached their accuracy goal, and they push it then to Amazon S3, to some storage bucket, where basically the production-ready models live. That means they want to continue towards production. So first thing they got to do is actually a lot of copy pasting. They copy paste a lot of their code out of the Jupyter Notebook to create the Python module, rewrite some code to establish their inference pipeline. So actually the thing that should be running in their microservice in the Kubernetes cluster. They of course also add some tests. In their case, it's mainly unit tests on code. And once that's done, they have this Python module tested, at least to some extent. They take that and go to the DevOps team and say, hey guys, could you please deploy this in our cluster? And the DevOps team says, yeah, sure, no problem. And they add it to the backlog. So that's the current process, how that works. At some time then in future, that model is going to run in production on the cluster. Of course, the data science team also says, there are a few things going wrong. So to be very honest, one thing is definitely right. We can't do scalable training. We train on our local computers. Machine data can be quite large. And we just can't leverage that. So that's a big problem they're seeing. Then also reproducibility. They just do not have any process or tool support to ensure reproducibility across experiments and also across data scientists. Of course, they say some data scientists take some notes in the Jupyter Notebooks, some markdown to actually remember what experiments they did and how they turned out. But to be honest, that's really not comprehensive, and it's also hard for other data scientists to read. Consistency is also a frequent issue. So they write their training pipelines usually in the Jupyter Notebook, and then they copy paste a few snippets of code and then rewrite a bit of a code to get to the inference pipeline, which is then deployed inside the microservice on the cluster. And of course, if they change small things in the training pipeline and they forget about implementing that also in the inference pipeline, that really results in their models predicting absolute garbage. That's a big issue. They're also aware that code testing is not everything. In a machine learning system, we're dealing with a variety of artifacts. So code testing is important, right? But it's not everything. You also need to think about testing your model, right? Their models could be, for example, biased towards certain machines. Imagine they have some anomaly detection running across a variety of different, very similar machines, but perhaps they have a bias towards certain machines in there. Or also they should consider data testing. So actually checking whether the data that comes in does look like what they expected to see. So far, they don't do that. They only do code tests, and they do not have any standardized procedure of and a code of conduct what they should actually be testing. Well, the handover, this is really something that hurts them a lot, because when they hand over the Python module to the DevOps team, well, for the DevOps team, it's not really a priority to get that model up and running on the cluster. You know, they add it to the backlog and they do it at some point, but to be honest, it takes them usually weeks and perhaps even a few months to get that model running on the cluster. And yeah, that's a big problem, right? Because if you wait months until you actually see your model running in production, well, that's really frustrating from a data science perspective, and of course also kills your iterations, right? Your iterations from experiment to production are essentially dead at this point. If you notice that something went wrong in production, you need to go back, change something, and then you need to wait another few weeks to redeploy that. This is an issue. Once things are deployed, well, you still need to think about monitoring. Acme, of course, they do some monitoring, but you know, the DevOps team is really only familiar with the classic software engineering side, and the data scientists are not very familiar with how they should set up the monitoring in the microservice. So what they do is just classic software monitoring, you know, if you could say that. So that's the classic things such as response time and uptime, for example. They do not actually check whether the input data changes, whether, you know, some machines produce data that's something that doesn't look like what we've seen before. So obviously, there are quite some pain points in this process. But at the same time, right, this is not an especially bad machine learning development process. To be honest, this is fairly standard. This is something you see probably in 75% of organizations. Yeah, some organizations not even making it to the deployment stage at the very right. So this is actually, I would say, quite a standard process, unfortunately, with a lot of pain points. But this is what it is. That's Acme's current development process and tech stack. So what would be a process that would actually really fit them, or a process where they would think, yes, this would really enable us to ship fast and ship often and ship safely? Well, fortunately, Acme's management, you know, they're really convinced of the potential value of machine learning. They say, yeah, you know, we really recognize that there are some really important use cases for us, especially when we look at cost reduction, predictive maintenance, and all that stuff. That could really save us a lot of money. So definitely, we want to invest in machine learning. We want machine learning to become a first-class citizen in our tech landscape. And that means, to be precise, that developing machine learning systems, at least from a tech support perspective, should not be any harder than developing a classic software engineering solution, you know, some backend service, for example. And that's a big thing, because what this means is that translates concretely that the data science team in the next 2 years, so we have some time, should come up with a best practice machine learning development process with end-to-end MLOps support. That's the objective. Well, of course, that's for the data science team, that's great news, right? They are very, very happy with that. They see big investment, actually, a big commitment to machine learning in the company. And they also get some budget to hire some consultants. And together with the consultants, they sketch out a process that could work for them, a best practice process, which kind of looks like this. Let's zoom in a bit more on that process and go over it step by step to actually, you know, understand a bit what characterizes such a, you know, best practice machine learning development process supported by MLOps. So let's start at the very left, where it says feature store, this green data store symbol. A feature store is something that is a quite common element in machine learning development processes supported by MLOps. I think feature store is actually, it's a fancy word. It's a fancy word for something that, for something relatively, at least at the very core, simple. It just means we want to have a central storage for all the features for the data that we use for machine learning. So basically, both at train time and at inference time and for data exploration, data scientists can always tap into this feature store. Typically, these feature stores have certain characteristics. For example, usually there is an online and an offline element to it. The online element making sure that we can serve features with low latency, which is especially important at inference time for some applications. And typically they also have an offline part. That means this is the part that's optimized for big batch loading, which could be relevant for train time, for instance. Also, some feature stores have the nice characteristic that they let you travel back in time. That means, for example, if you had customer data and you want to know what the customer properties were 2 weeks ago, you can query that specifically, right? So you could have a timeline for each entity in your feature store. Yeah, this is essentially what a feature store is, just a central data repository where we store all our features, and we can use them. Different teams can use them throughout the machine learning process. Typically, a data scientist, now at the very top left, starts his or her data analysis exactly there. They open a Jupyter notebook, query some data from the feature store, do some plots, do some statistics, so they get some idea of the data. At some point, they say, all right, let's start with some experiments. And an experiment, is a word that describes, I want to do some pre-processing, some model training, some model evaluation, essentially, to see, how good are my models actually. Well, in that process, the small difference is that we are doing these experiments in an orchestrated way. And that means concretely, typically you would chop up your experiment in different stages and different steps. And these steps are wired together in a DAG. Yeah, so you have a sequence of steps that characterize your experiment, typically starting with a data extraction step, then some data validation, perhaps model training, model evaluation, and so on. Also, usually part of such an orchestrated experiment is quite meticulous tracking. This means we track exactly what goes into each step and what goes out of each step, and which parameters are used within each step to really enable us to get a very, very comprehensive picture of what this experiment exactly looked like. Yeah, this is important for ensuring reproducibility. Even if you did an experiment 2 weeks ago, you can always hop back and see what exactly happened and what results you got out of it. And that's super important in experimentation phases. Well, so our experiment, our data scientist does experiments. He does, let's say, 10, 20 experiments. And at some point he thinks, yes, now I'm happy with that. My model seems to be good. It seems to be robust. I want to go to production with that. So he, for example, checks in the code for his best experiments he wants to take to production, to the master branch. And then an automatic build process is kicked off. Then we are building that pipeline, we are testing it, we are packaging it, and we are deploying it. We are deploying it to some computational infrastructure. That could be a Kubernetes cluster, could be some computation server with a few GPUs inside, whatever, right? And there, this automated pipeline, this big blue block in the middle, then lives. Yeah, it's essentially a job that can be triggered. Inside that job is exactly what the data scientist defined. It's exactly these steps he or she defined. Such a pipeline can be triggered then. It can be triggered by multiple things. It could be triggered by time. So let's say every Monday, 6 a.m., we're going to run a training. Or it could also be triggered by performance metrics, some accuracy metric dropping below a certain threshold. Then we're going to retrain on the newest data. Or it could also be triggered by the push of a button. That could also be possible. When that pipeline is triggered and it runs, it's going to output two things. First of all, it's going to store metadata into this metadata store, the big gray storage symbol a bit below this automated pipeline. So such a metadata store, I think it's also a fancy word for some kind of database, essentially. You could use a Postgres database here, whatever. There are also a few specialized feature stores, though. Typically, what we store in there is any metadata, any information we get from that pipeline run. So when did that pipeline run? Why was it triggered? Which steps were included in that pipeline? Then perhaps also evaluation metrics, what the model was called that came out of that, and. So essentially everything that could be of interest to us about this pipeline. Again, to ensure that from an outside perspective, we knew exactly what is happening. The second big output that this pipeline produces is, well, of course, a model, a trained model. And that model is being checked into a model registry. A model registry, again, is some kind of data storage that takes models, right? That stores models. At the simplest form, this is some blob storage, some Amazon S3 bucket. You could call that a model registry, even if it's doesn't really have much support for storing anything but your models and other files. But there are also a bit more elaborate model registries that are specifically optimized to store your models, to help you version them, help you manage them, and also perhaps store certain types of evaluation metrics together with these models. Yeah. Well, once your automated pipeline training run is finished, it also kicks off model serving, the deployment of model serving. It basically tells the deployment part of the model serving, hey, there is a new model, please redeploy my prediction service and get that new model, by the way, from our model registry. So that's what happens. Our prediction service is redeployed, loads the newest model, and then it's working. And it's, of course, outputting predictions. But next to that, it's also providing metrics. So what's going on? What does the data look like that's going into that service? What do my predictions look like? Perhaps if I can, how does my prediction accuracy develop over time? Yeah. So this was a lot of information now, and it's a quite a it is quite a process, right? Such a full best practice machine learning development process powered by MLOps. So what are the key takeaways here? I think it's first super important to highlight that what we've seen now, this process is complex, but the big difference to the complexity to what we've seen before is that from a user perspective, from a data scientist perspective, this process is actually not complex at all. Because what the data scientist touches here is very limited. The only thing that the data scientist really cares about, or that he needs to take care about in this process, is designing the experiment. That's the only thing he touches. And typically, that's also what data scientists like to do. And usually that's also what they are best at, what they're trained as, designing experiments that deliver models that work. So basically a data scientist only touches this left top part of this process. All the rest is actually fully automated by your MLOps platform. Yeah. And this is really where we can see the strength of MLOps. We have this complex process, right? We recognize the complexity, and we try to abstract away from this complexity for the user by really rigorous automation throughout this process. This is really the key behind such a best practice MLOps setup. That sounds great. So we have our target process now. That's a big step done. And also I think here it's important to note, right, such a target process, such an objective process that could look a bit different for any organization. It always depends a bit what exactly are your use cases, what exactly do you want to achieve. Also, what is your maturity from an organizational perspective? What we've just seen, what Acme wants to implement, that's a big step. That's really a best practice process. So right, having such a process is nice, but eventually you always need a tech stack that actually powers that process. Let's quickly hop back into this diagram again. When we went over this diagram, we saw a few things, right? We saw a few tools that we need to choose. For example, we need to choose a feature store. We have a variety of different options there. We need to choose how we're going to orchestrate our experiments and also how we're going to track our experiments. Of course, we need to choose a source repository. That's probably an easier choice. And then we need to choose how we will do our CI/CD pipeline. Also, what are we going to use as a model registry? Right, we've heard they're very simple options, but then there are also quite sophisticated model registries. We need to think about what should support us to serve our models, where do we want to store our metadata, and also what tooling do we want to use to track our performance. And these are by far not all the choices that we need to make in to build a tech stack that supports such a process. So perhaps you might think, well, there must be a dominant stack, right? It can't be so hard to make these choices. There must be a stack that 90% of companies use, and we can just go with that. Well, the unfortunate truth is that when it comes to MLOps, that's not the case. There is no dominant stack. There is not the MLOps stack because, well, this field is very new. And it has been under incredible development, under incredible flux over the past years. Yeah. So of course, there are some players that are a bit more established than others, but it is important to understand that this ecosystem is under such a flux that essentially every week you have new packages pop up, new tools pop up, gaining support very fast, other tools getting deprecated, merged with other tools, big players stepping into the game. And then you do not only have this plethora of tools, but what you also have, but what you also face is that these tools, in some aspects, they're very similar, but then in other aspects, they're incredibly different. You have tools that you can use to essentially build your entire platform around, right? They basically deliver everything you need, or almost everything. And then you have tools that only do one thing very well, but that really very, very well and very deep. Then you have tools that are made to be used by data scientists. For others, you need deep MLOps knowledge, and. So these tools really, they differ in so many different dimensions that it makes it really hard to make appropriate tooling choices. So what Acme does is they recognize this, right? After some research, they see, wow, okay, we have found 50 blog posts, everybody recommending a different tool for this and that. That sounds really complex. So what they do is exactly what you should do. They start structuring information. They start trying to ask the right questions. They need to actually make the right decisions. And for that, they use something very pragmatic, an MLOps canvas. Such a canvas, you've probably seen different canvases throughout your career. This one is one that's a bit more tailored towards MLOps, and it helps you ask questions and structure information. Questions such as, okay, how does the tool actually add value to your process? Does it save you time? Does it improve your quality? Why do you actually need it? Also, how does it integrate into your infrastructure? That's one thing, but also how does it integrate with other steps in your machine learning development process that you've sketched out? That's a tricky one because some tools, they're made to work together essentially. And then there are tools that will require you to write tons of glue code to actually make them work together. Also, you should be aware of your diversity of stakeholders. You might think that the choices you make, well, they impact, of course, your MLOps team and perhaps your data scientists, but that's not quite the case. The tools you pick might have a lot wider impact, might have impact on the ability to actually explain your predictions. They might have impact on how you can actually deploy and which infrastructure is the right one. Also, it's important to recognize that different packages have different needs for skills. So depending on the tool, you're going to need very different skills for setting it up, for maintaining it, and also for using it. There are tools that are made to be used by data scientists, and then there are tools that require very deep knowledge of DevOps or MLOps, for example. So Acme, they do their homework. They do that, right? They fill out 20 of these canvases, they do the tooling research, and they really spend a week doing this. So they have the feeling, yes, we can now make our tech decisions. We can essentially put some fancy logos on the process and we can start building that platform. However, also they see that, well, there is an elephant in the room. Specifically, they have the feeling that they keep stumbling upon this big strategic question here. Are we going to build our platform in a custom way, or are we going to build a managed platform? And are we going to use a managed platform? And that's an important question to ask. Yeah, that's a difficult one. That's going to tie you down for years to come. So what they do is they sketch out two scenarios. First, they sketch out the custom scenario, right? What would happen if you build a platform by wiring together different tools? And that's what it kind of looks like. You can see a few fancy words here. MLflow, probably that's a very popular package for experiment tracking and also as a model registry, for example. Kubeflow for pipeline orchestration. Hopsworks as a feature store, and. You can see you're gonna have to wire together a lot of things. On the other hand, a managed platform is quite different here. It's basically they say Amazon SageMaker could be a reasonable choice, so let's go for that. Let's have a look at this, and you can see SageMaker essentially delivers you what you need throughout your process, and even what you can't get from SageMaker, you find in the AWS ecosystem somewhere else, right? That's a very classic example of a managed platform. The real choice then burns down to a few dimensions that you should pay attention to. Not all of them are listed here, but some important ones are listed here, such as process integration. With a managed platform, getting everything out of one hand, you will have a very smooth experience. On the other hand, building a custom platform, that's never going to be as smooth, probably. From a cost perspective, well, that could be very different. Managed platforms sometimes have a pay-per-use model. They often do not require a lot of upfront investment, not always though. Building a custom platform, you need to hire a dedicated team, a lot of upfront investment, and that's going to be quite costly. Also, the skills you require for building a custom platform are very, very rare. Yeah. And however, the flexibility you get from building a custom platform is really that you get full flexibility. You can really tailor it to your use cases. So that could make sense if you have very specific use cases that a managed platform does not accommodate to. Also, you're not going to face a lock-in, right? Your platform is not going to lock you in. Some specific packages might do, but it's always easier to swap out a specific package than actually change platforms. If you want to change from SageMaker to, let's say, Google's Vertex AI, well, that's going to definitely be quite a challenge. For Acme, this choice is relatively clear. They say, well, we really want to go for a managed platform, for SageMaker, to be honest, because they say, well, our long-term IT strategy is based on AWS anyway. We want to become cloud native on AWS. So the lock-in doesn't really worry us. Also, we believe that SageMaker really is top-notch, and Amazon has big stake in it. So they're going to stay top-notch for the next few years. They also do not really require much flexibility. They have their use cases, but they are fairly standard. And eventually they also say, well, we have 6 data scientists, and in 2 years it's perhaps going to be 12, but we don't want to hire a team of 5 people to build a platform that's going to be used by 10 people. That just doesn't pay off for them. So the choice is fairly clear. And this is also how we get our tech stack in that case. So we have our process now, and we have mapped our tech stack onto that process. So we roughly know what tools we now need to support this development process. Lastly, right, we need to define a transition strategy. So how we actually go from what we currently have, this inefficient manual process, to a best practice process with MLOps. Acme says, well, we really want to do a stepwise transition. So we want a stepwise incremental layer our tool stack, starting by changing the aspects of our current process that really hurt us most, that go wrong terribly, perhaps. And by doing this, by first tackling the things that go wrong a lot in our current process, we can relieve these pain points fast and quickly get value out of it as well. Also, this stepwise transition, step by step changing our process, introducing a new tool, we give our team time to accommodate to it, to get familiar with it, and we also minimize business disruption, right? Our data scientists, they can keep working essentially. Concretely, for Acme, this means that they will start with the big pain point of fixing this very expensive handover. The handover from data scientists to the DevOps team that cost them weeks and months. What they're going to do is they're going to switch that first. They're going to switch from deploying at the local Kubernetes cluster to deploying on SageMaker. And this is fairly easy. This means that the data scientists now actually have the deployment and serving in their hands, and they can speed up going from experiments to production big time. So that's our transition strategy. Step by step, we're going to layer our tool stack. We're going to change our process to eventually end up with our target process over the course of 1 to 2 years, right? And by taking this first step of this transition strategy, we already do a highly important thing. We bridge our deployment gap. We can now quickly go from experiment to production, or at least the deployment barrier does not hold us off anymore. With every additional step they are going to take, their process will become more efficient and more automated, and therefore already also limiting human error, right? And eventually, they will get incredibly fast iterations out of it. They will be able to ship machine learning systems within hours or days instead of weeks, months, or perhaps even a year before. And this is exactly what you need. You need to ship fast, ship often, and ship safely for machine learning systems to really contribute business value. I hope you enjoyed the talk and you learned a bit about machine learning operations and why it's so critical to really get the value out of your machine learning systems that you would like. If that topic interests you, and perhaps not only this topic, but in general, if you're a curious engineer and you're interested putting your work to play to create the world a bit of a better place, then also check out what we are doing at Transaction Monitoring Netherlands, tmnl.nl. We are hiring big time to build a worldwide unique transaction monitoring platform. Also, of course, if you have any questions regarding the talk, feel free to send me an email. Always happy to get in touch, perhaps via LinkedIn as well, and we can exchange a few messages or go for a virtual coffee. Thank you very much.
Thank you, Simon. Unfortunately, we are out of time. There are a lot of questions, so I suggest that people connect with you either here in this app, on Swapcard, or write you an email. So if you missed the email, just rewind the video a little bit, and there you find Simon's email. That being said, thank you a lot, and I hope to have you at some time again to get to the next stage of MLOps and how to make the world a better place.
Thank you very much for having me.
Thank you.
Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now.